Hello friends, welcome to lecture 2 of EMT for BSc and MSc students. Here today we are going to discuss about how to convert Maxwell's equations, integral form of Maxwell equations to differential form, and how to convert differential to integrals. Okay, so we are going to discuss those things in this video. Okay, so now you see a link of the first lecture is given in the description box. If you haven't watched, then please go through that. And before we start, please subscribe the channel if you are new to my channel and inspire me to create new contents for you. Help me to grow my channel. And hit the thumbs up button, also share with your friends, and hit the bell icon as well so that you get notified when new video will be uploaded. So now let's start. So these are the Maxwell equations. On the left hand side we have integral forms, and on the right hand side we have differential form. Right, now let me show you how to convert this integral form to differential and differential to integral. Right, so let me show one by one. Let me take the first equation first. The first equation is integration, this is surface integral E dot ds and cap is equal to q in, that means charge enclosed by the closed surface, by epsilon naught. Right, so hope you know the meaning of epsilon naught, that is permittivity of free space. Right, so here you can see in order to convert to differential form, so let me apply the Gauss divergence theorem. Right, so before that, here you can see what we're going to do, that the volume charge density rho is given by, let me write here, volume charge density rho is nothing but uh, charge by volume. Suppose we have a very small element of volume, we have very small volume element dv and charge enclosed by it, suppose dq, then rho will be equal to dq by dv. So dq will be equal to rho dv, then uh, total charge will be obtained by integrating this, then what you will get, q integration, that will be volume integration rho dv. Right, so that's why this equation we can write like this as well, 1 by epsilon naught q in can be replaced by volume integral rho dv. Right, so here we have surface integral, here we have volume integral, so that's why let us apply the Gauss divergence theorem to convert this surface integral into volume integral. So volume integral del dot E, according to the divergence theorem, now it's become volume integral, right, dv 1 by epsilon naught rho dv, volume integral rho dv. So here we have applied Gauss divergence theorem, right, so this is Gauss divergence theorem. And if you compare the both right hand side and left hand side, here del dot E will be equal to rho by epsilon naught. Right, integral and dv, that volume integral will be, if you removed the volume integral from both sides, you can write del dot E, that's gonna be equal to rho by epsilon naught. Right, so this is differential form. Right, this is differential form. So here you can see this this also can be written as del dot E epsilon naught, E into epsilon naught rho. So E into epsilon naught is denoted by capital D. Right, we can write this also. Okay, if you keep this equation in this form, then also correct. Right, so now in order to convert this one into the integral form, what we're going to do, just we're going to reverse the order of this all these steps. Okay, so we're going to start from this equation, then we're going to take a volume integral on both sides, then we're going to apply the Gauss divergence theorem to get this theorem. right, to get this surface integral, right? That's how we're gonna go from the differential to integral form. So this first equation is done. Let me show you the next equation, how to convert this integral form to differential, differential to integral. So if you know the if you know how to convert the integral to differential form, then just reverse the order of the steps to get the integral form, right? So hope you have understood. Now let's move on to next equation. So here you can see the next equation is this. So let me take this equation. So the next equation is the surface integral b dot ds. This is nothing but Gauss law of magnetostatics, right? For magnetic field is equal to 0. Again, convert this surface integral to volume integral. That volume integral, that's gonna be del dot b dv is equal to 0. So here again, we have applied the Gauss divergence theorem, right? Divergence theorem, right? Gauss divergence theorem. So if you compare the left hand and right hand side, here you can write this is equal to 0. Okay, so again, in order to get the integral form, just reverse the order of the steps, then you're gonna get integral form from the differential form. Hope you have understood this. So this is the differential form, right? Differential form. Now let me show you how to convert the third equation into differential form. So here you see the integral form of the third equation is this. This is the integral form of the third equation, which is nothing but the Faraday's law. Now let us convert this one into differential form. So let me take that equation as well, right? So here is the third equation. Line integral e dot dl, right? E dot dl negative partial derivative with respect to time of the surface integral b dot ds and cap. So in order to convert the line integral to surface integral, on the left hand side we're gonna convert this line integral to surface integral, right? Surface integral using the Stokes theorem, that is curl of E. Now it's become surface integral, right? ds and cap. So here we have applied Stokes theorem, right? Stokes theorem. So here you can see this is also surface integral, this is also surface integral, right? So now if you compare the left hand side and right hand side, so curl of E will be equal to negative partial derivative of B with respect to time t. So to come from this step to this step, we have applied Gauss theorem, right? So here we have E. If you want to convert this line integral into surface integral, just here we need to take curl of E, that means del cross E, right, instead of E. So hope you have understood this, right? So now let me clean these things, right? Here you can see now. So comparing left and right hand side, we're gonna get curl of E is equal to negative partial derivative of B with respect to t, right? So this is the differential form. So again, to convert this differential form to integral form, just reverse the order of the steps. Write this one is this is step first, then next this one, next this one. Okay. So hope you have understood this. Now let's move on to the fourth equation. So that is the Ampere's law, which was modified by Maxwell, right? So let me scroll down the page. So here is the fourth equation. Line integral b dot dl is equal to mu naught surface integral vector z epsilon naught partial derivative of E with respect to time t ds, again surface integral. Again, convert this line integral to surface integral. Now use Stokes theorem to convert this line integral to volume integral, right? So sorry, surface integral. Convert this one into surface integral using Stokes theorem. So in order to convert this one into surface integral, we need to take curl of B, right? That is del cross B. Now it becomes surface integral mu naught surface integral z plus epsilon naught del E by del T ds, right? So remove the surface integral from both, then comparing the right hand and left hand side, we're gonna get curl B, that's gonna be equal to mu naught z plus epsilon naught del E by del T, right? Del E by del T. So this is the differential form. So here we have applied Stokes theorem, right? Now to convert this differential form to integral form, just reverse the order of the steps, right? So hope you have understood. So see you in the next video. So now you see, please subscribe the channel if you are new to my channel, and share with your friends if you think these videos are helpful, and hit the thumbs up button as well as hit the bell icon so that you get notified when new video will be uploaded. So see you in the next video. Thank you.